Good morning, students. And today we'll be working on another algorithm, and it's called k-nearest neighbors. This is a very classic, very simple algorithm, yet at certain scenario is surprisingly effective. So let's take a look. So here I prepared a picture and quickly illustrate the idea of k-nearest neighbors. So the idea is that if we got some samples with 4 classes, and we have a sample that we want to predict whether which classes it belongs to, we can just take the nearby neighbors, for example, 3 or maybe 4, let's say 1, 2, 3, 4, who are the nearest. We can say that this cross is probably belonging to these blue classes. Or we can choose, let's say, the nearest 7 neighbors, right? So it could be this, and maybe that, right? But if you take the majority, there's 4 to 3, right? So this cross is still 3, right? So the number of neighbors we refer here, we use a notation called k, right? So yeah, so k nearest neighbor, there are really no any equations. It's just that simple, and at certain cases is surprisingly effective. So then based on its effectiveness, what is the potential limitation? Well, because you need to find the nearest neighbors, you need to basically calculate the nearest distance between this x with almost all the points, right? Which is actually very, very costly. So that could be one potential limitation of k nearest neighbors. So let's take a look what we're gonna do today. So here I already prepared you the code for running the data. We'll be writing a function to first calculate the pairwise distance between the given sample with all other points. We'll then sort all the pairwise distance, and then finally maybe sort out only a certain number of neighbors, and then get the majority class of all the neighbors. And then finally, we'll be applying all this function together and try to use it. All right. So let's start right now. So here I have prepared, so let me make sure that I clear all the outputs, restart, and maybe run this again. And here's my data. I'm using a function called makeblobs in this time, and there are 300 samples, and there are a total of 4 centers. Each of them, the STD is roughly 1.1, right? Which refer to the spread of the circle. So let's run this. And then here's our samples. And I also then do some trend test split and scale them. So now let us write the function for pairwise distance. So let's do this. And I'm going to call this distance. And X train is basically all the samples here. And I have X test, in which is also a list of samples. So I need to find the pairwise distance between this and this, so that I can list down all the nearest neighbor for each of the sample inside X test. So what I can do is basically the distance is nothing but X test. And I'm gonna create a new column right here, minus string np dot new axis. Yep. So the reason why I create a new dimension, so that when we can minus, it can broadcast, and then so we can have a distance, a pairwise distance. And then finally, based on the distance formula, I also need to square them, right? So I can do a square, right? For those who wonder why we need to square, it's very simple, because regardless of the distance, is negative or positive, if we just square them, then it doesn't matter whether the sample is on bottom or on the above, right? We just want something that is nearest, right? So square actually give us that effect. And finally, we can sum the distance. So axis 2 is basically referring to the features, right? So here I need to find a distance, the minimal distance on the x-axis and also the y-axis, right? And that axis is nothing but this dimension, which is the features, right? So that's why I sum across all of them. And then finally, I do a square to get back, to cancel this effect, but still positive. So np dot square root some distance. So basically, we are doing something like square root x squared plus y squared, the Euclidean distance we learned in high school. All right, so now we got the fine distance, and definitely we can try whether this really work out. So let's say that I have some example of train, and let's say I have 3 samples. And so this is the XY coordinates of each of the 3 samples. And then I have test EX. And what I want is I want the pairwise distance between this and this, right? So what I can do is I can run and test whether it works. So I'm going to say train X and test EX. And then finally I can print D. And I can find that, wow, so between the, so what we get is the distance between this and this, right? And this and this, right? And this and this, sorry. And so first of all, this and this is this, right? And this and this is this 0, right? So yep. So hopefully that would be the how the fine distance work. All right. All right. And as you can see, if you look closely, this actually represent the distance between this sample with all these 3 samples, right? So if we just take the smallest distance, we know that the shortest distance of this sample is nothing but the second and the third sample, which is this one. So if we can find that out, then we can try to find the majority class of these 2, and then that should be the answer. Similarly, you can notice that this one is the distance between this sample test with these 3 samples, right? And it's very obvious that the first sample has the shortest distance with this, right? So we can take the class of this, and then could represent could be the class of that, right? So that is the fine distance. And then now we can, based on that, we can do this arc sort, which help us to determine which one is really the shortest distance. So I can find neighbors, X train, X test, K go tree. And I'm gonna say, first of all, please find the distance between X train and X test, right? And then what I can do is neighbors Ix equal to np dot arc sort distance. And what I can do is I can say I want k number of index, right? And the return neighbors by x. If I'm not wrong, this one will just give me the smallest to the greatest. So if I do that, I will probably rank, right? So I can do this, and why not we just try it on this right away, right? Because we already have this D. So we can replace this with D. And let's say we want the top 2, right? So we can enter, and we can list this down. And we can see that for the first one, the smallest neighbors is nothing but 1 and 2, which is this one and this one. And for the second sample, the one with the least shortest distance is 0 and 1, which is this one. And because this one and this one is the same, we just take both of them, right? Great. So it seems like we are able to write this function. So now once we get this, we need to get the majority class of this, right? And then, of course, we can write a for loop, but here I'm going to introduce a very simple function called nb.beanCount. So let me first write it down. Get most common y, right? Return np dot bin count y dot argmax. All right, and later on, let me introduce them. How does it look, right? But let me just punch it down first, and then here I will be just writing. For example, let's say I have an array of, let's say a equal to np dot array, and I say I have 0, 1, 1, 3, 2, 3. Anything should be fine. 3, 7, 2, 2, 2, 2. Okay, so let's say I have this array, and then what I can do is I can say that count equal to np.bin count. A and min length equal to 10, and I can print the count, and you can see that this is a very nice representations, right? Because I can see that for 0 I have 1, and for 1 I have 2 of them. For 2 I have 5 of them, right? And for 3 I have 3 of them, right? So bin kind actually give me a very, very nice count here, and simply I just get the index with the highest count, right? That could already give me the classes that I want, right? Great. So now what I can do is I can say the most common is equal to count.argmax, right? Which again will give me the position, not the. So for example, here I got that 2 because arc is mostly related to the position, right? Sorry. And then finally, we can do also arc sort, right? Equal to count.arcsort, right? And in here, this is basically ranking from the smallest index. So from 4 and the highest index, which is 5, has the biggest majority, right? So for example, if I am interested in the second most common, I can certainly put -2, and then oh, sorry, I should not do like this. I should put -2 here, and then I can know that okay, give me 1 second. Clear all, restart run all. All right, and this, okay, I should do count, right? I should do arc sort. Just give me 1 second. Here. Yep. Yes, and okay, I forgot this column, right? Am I right? Yep. Right. So you can use this notations to get whatever you want, right? Okay, great. So now we can write a wrapper function that links all the functions together, right? And recall that I have this X train and Y train that I have prepared up here. Okay, so first thing first, what I'm gonna do is I'm gonna create a function called predict, and I have x train, x test, and y train, and k equal to 3, right? And I'm gonna bundle everything. So first of all, what I'm gonna do is a neighbors index equal to my neighbors and k, right? And inside this find neighbors, you'll call the function find distance, and then return me all the nearest neighbors. And then what I can do is a prediction is equal to x test dot shape 0. So we want the prediction for that number of tests sample, and then we're going to say that for ix y, and enumerate y train neighbors ix. Okay, so we need to check for that index, we want to check the y, all right? And then we're going to say that predict ix is nothing but equal to get the most common index of this list of y, right? Because when you say y train neighbor ix, this is a list of index, right? So we just simply get the most common index, right? Which is nothing but the argmax right here, right? Which is this one. All right, and then nothing, you just return the predict, and that should be it, right? So now let us do this. So we're gonna say y hat is equal to predict x train, x test, y train, and let's say k equal to 3. And now we're gonna try to list the y hat. So this is our prediction, right? Now we want to actually print the classification report, right? So what we can do is from sklearn.metrics import classification report, and now we can say that classification report is y tests and y hat. All right, so I should do print to make it very nice. All right, so you can see that, wow, it's surprisingly good, right? That using k nearest neighbors, it was able to predict with almost 89% accuracy, right? So at certain cases, k nearest neighbors is surprisingly effective, right? Yep, thank you very much, and see you in the next classes. Bye-bye.